lots of interesting stuff today. And by the way, we did finish 9.3 last time, actually, or I did at least. Basically, I'm kind of repeating the instructions from this past Tuesday. Now, today is Thursday, December 3rd. I know it's easy to forget the date, but today is Thursday, December 3rd. It's Thursday, December 3rd. We're near the end. It's day 30. All right. We finished 9.3 last time, actually. Today, we're going to do 9.4 on induction, which is an interesting topic, but you really have to be patient with it. Once you get it, it's great and it's cool, but it's a leap of faith. 9.5 is the binomial theorem. It's like cheat codes. My students love it. And we'll start with ellipses in chapter 10. All right. And remember that the course evaluation link expires tomorrow if you'd like to submit that. Thank you. And remember that the homework for chapters 7 through 10, we're going to discuss that for part of Tuesday, basically all of next Thursday. And the homework and the Alex extra credit will all be due by midnight, Monday, December 14th. So you do have a couple of weekends to work on that stuff. All right. So any general questions before we proceed? Oh, and don't forget, that last homework assignment is 250 points. It's worth a lot. It's worth a whole lot. So make sure that you do a good job on it. That's one reason why I want to give you some time. Any questions before we go on? It's really cool stuff today. So lots of good concepts going on and some cool videos. Questions? All right, so let us begin. And we're going to start with a fun stamps problem, actually. So let's begin.
Hi, everyone. Let's start section 9.4 on proof by mathematical induction. It's a method of proof. And we're going to start with a humble stamps problem. You might think this is strange, but this is actually a kind of problem you see in computer science classes, including discrete math, like Math 245. Here's my claim, and there are various stamps problems like these. But here's my claim here. I can construct any integer amount of postage of 6 cents or more by using just 3-cent and or 4-cent stamps. So if I had a machine, like a counterfeiting machine, shame on me, that can produce infinitely many 3-cent stamps and infinitely many 4-cent stamps, I make the claim that if you give me an integer number of cents, 6 or higher, I can construct that amount of postage by just using these stamps. The idea here is that we're going to figure out what strategies we're going to use to get from n cents to n plus 1 cents, where n is at least 6. So how do we get how do we start with getting 6 cents and then moving to 7 cents, 8 cents, 9 cents, and so forth, forever and ever and ever, 1,000,000 cents, 1,000,000,000 cents. So we're kind of thinking of climbing a ladder, or in this case, the way I've typed it, descending a ladder down into the depths, that deep descent. First of all, we need to start with a basis step. Now, my claim begins with the case of 6 cents. All right, just constructively, how can we get 6 cents of postage by using 3-cent stamps and or 4-cent stamps? Well, I would use 2 3-cent stamps. You can see, by the way, that there's no way of getting 5 cents from these. So you can see why I started with 6 cents and not 5 or lower, because you cannot get 5 cents from these stamps. But 6 cents, you can construct that by taking 2 3-cent stamps. Now, here's the way to look at it. Instead of just going constructively, okay, how can I construct 7 cents? Think of it this way. Again, what strategies do we use to get from n cents to n plus 1 cents? So taking a look at this configuration for 6 cents, what can you do here in order to add 1 cent to the total value? How can you go from 6 cents to 7 cents beginning with this configuration? Well, we would keep one of the 3-cent stamps, but then we would convert one of the 3-cent stamps into a 4-cent stamp. So we're descending that ladder. How do we go from 7 cents to 8 cents? Well, we'd keep that 4-cent stamp and we change the 3-cent stamp into a 4-cent stamp. So one of the strategies seems to be, if you have a 3-cent stamp, exchange it for a 4-cent stamp. That seems to be an easy way to go from n cents to n plus 1 cents. Again, to go from n cents to n plus 1 cents. If there is a 3-cent stamp in your current configuration, trade it in for a 4-cent stamp. Trade the 3 in, whoops. Trade a 3 in for a 4 here. Trade this 3 in for a 4 here. But now wait a minute. When we go from 8 cents to 9 cents, unfortunately, we don't have any more 3-cent stamps. Are we stuck? Well, not necessarily. How would you construct 9 cents? Well, let's take 3 threes. 3 3-cent stamps. And you see that when we exchange 2 4-cent stamps for 3 3-cent stamps, then we're trading in 8 cents for 9 cents, and we're gaining a cent. So that seems to be another strategy. If you have 2, or I'll say this, in the absence of 3-cent stamps, so if there are no 3-cent stamps in your current configuration, like this one for 8 cents total, in the absence of 3-cent stamps, you know you have at least 2 4-cent stamps. So if you don't have any 3-cent stamps, you know that you have at least 2 4-cent stamps. You know that you don't just have 1 4-cent stamp because 4 cents was not included in this, right? We're looking at amounts of postage, 6 cents or more. 4 cents is not part of the game. So if you have a configuration with all 4-cent stamps, you know you have at least 8 cents. You have at least 2 4-cent stamps. So in the absence of 2-cent stamps, you know you have at least 2 4-cent stamps. Trade in 2 4-cent stamps for 3 3-cent stamps. And together, these two strategies will allow you to go from n cents to n plus 1 cents for any integer number of cents that's at least 6. Let's do it, all right? How do we get 10 cents? We keep 2 of the 3s, but then one of the 3s goes to a 4. We trade the 3 in for a 4. How do we get from 10 cents to 11 cents? We can keep a 3, keep a 4, but then trade in this 3 for a 4. So we now have 1 3 and 2 4s. That's 11 cents total. 12 cents. Trade in the last remaining 3 for a 4. 12 is 4 plus 4 plus 4, or 3 times 4. Wait, now we've run out of 3s. Well, I guess you could also reimagine this as 3 plus 3 plus 3 plus 3, but let's build on this. Let's build on this configuration. We have 3 4-cent stamps here. Remember, we can trade in 2 4-cent stamps for 3 3-cent stamps. Move this, oops. We can trade in 2 4-cent stamps for 3 3-cent stamps. And then this 4 goes here. This last 4-cent stamp goes over here. Of course, the order does not matter. Addition is associative and commutative. All right, so again, the 2 4s become 3 3s. We go from 8 cents here to 9 cents here. This 4 stays put. So we go from 12 cents to 13 cents over here. 3 plus 3 plus 3 plus 4 is 13. And then you can start changing 3s into 4s and so forth. So you agree that with these two, with this basis step, together, 6 is 3 plus 3, together with these two strategies, we can then produce and construct any integer number of cents, 6 or higher. 6 or higher. You can construct 1,000,000 cents, 1,000,000,000 cents, your social security number, whatever. So if you understand this, you're well on your way to understanding induction. And that's a really critical thing, being able to understand induction. Some people take a long time to understand it. Many people never do. Okay, so I'm going to show you a couple of videos that are really going to get at the core of induction. You'll see.
Any questions before I show you some fun videos? I'll show you the point of this in a moment. It's a method of proof by induction. Any questions thus far? Any questions thus far? Well, in the meantime, I'll keep the chat on. I want to show you some videos. This is induction. Pause this. All right, let's discuss that problem.
All right, folks, let's do the handshake problem. Imagine n+1 people. I know Josh Hutcherson, or whoever the guy's name is, was using n people, but let's now imagine n+1 people walking into a room one by one, where n is a positive integer. As each person walks in, that person shakes hands with each other person currently in the room. How many handshakes are there? Let's look at 3 ways to count them. All right, method 1. Again, imagine n+1 people walking into a room one by one. So person number 1 walks into the room and has nothing to do. Let's say that this is the room. Here's the room. Person 1 has nothing to do, waits for people to come in. But then person number 2 comes in and says hi to person number 1. Person number 2, person number 1, they shake hands. Then person number 3 comes in, shakes hands with both person number 2 and person number 1. Then person 4 comes in, shakes hands with person number 1, person number 2, person number 3. And so on and so forth. And then person number n+1 comes in. You can imagine them wearing jerseys with the number on them, right? Person n+1 comes in and shakes hands with the other n people in the room. 1, 2, 3, 4, and so forth. So what's a way of expressing the number of handshakes that take place? Well, person 2 shakes hands with person 1, that's 1 handshake. Person 3 shakes hands with 2 other people, 1 and 2, that's 2 more handshakes. Person 4 shakes hands with 3 people, that's 3 more handshakes, and so on and so forth. Again, person n+1 shakes hands with n other people. So this is one way of expressing the total number of handshakes. It's the sum of the first n positive integers. It looks pretty nice, but the problem is that ... the ellipsis. The problem is that this thing is not a closed form formula. There's a ... ellipsis thing in there. It's not a closed form formula. We would like a closed form formula for this. What is this equal to? The sum of a finite arithmetic series. What's this equal to? The sum of the first n positive integers. All right, let's look at 2 other methods for counting the total number of handshakes, because the numbers that we get, the expressions we get from all 3 methods should all equal each other. Let's go on to method 2. Imagine, once again, n+1 people in a room. So the people have entered the room. We have a room with n+1 people in it, and they've all shaken hands. Each pair of people have shaken hands. Let's say they've already done it. Okay, so here's the idea. Each of these n+1 people, let's say n+1 is 5 for now. Each of these n+1 people shakes hands with n other people. So if we have 5 people in the room, then each person has shaken hands with 4 other people. But the problem is that if you look at it that way, this double counts because we're counting person A's handshake with person B and person B's handshake with person A as different handshakes when we shouldn't be doing that. So we have to adjust for that double counting. So here's the deal. Person 1 shakes hands with the 4 other people in the room. Person 2, person 3, person 4, and here person 5. Okay. Person 2 shakes hands with, person 2 shakes hands with person 1, but we don't want to double count that, right? But shakes hands with 3 and 4 and 5. Person 3 shakes hands with person 1, but we've already counted that, and person 2, but we've already counted that. Person 3 shakes hands with 4 and 5. We've already counted person 4's handshakes with 1, 2, and 3. Person 4 only shakes hands with person 5.
Next.
And by the time we get to person 5, we've accounted for all the handshakes. But once again, imagine the n plus 1, or in this case, 5 people in the room. Okay, n plus 1 is 5 in this case. Each of the n plus 1 people shakes hands with n other people. Each of these 5 people shakes hands, or they've shaken hands, with 4 other people. So each of the n plus 1 people has shaken hands with n other people. So we think there are a total of n times the quantity n plus 1 number of handshakes. But the problem is that along the way, we're double counting. If person 1 shakes hands with person 2, then person 2 has shaken hands with person 1 at the same time. So we're not supposed to double count this. This scheme up here double counts that. We don't want to count 1 shake with 2 and 2 shake with 1 as different handshakes. We want to count them as the same handshake. So we divide by 2. Because if you just take this product up here, you're double counting all the handshakes. We only want to count the handshake between 1 and 2 once. We only want to count the handshake between 3 and 4 once, and so forth. So the total number of handshakes is given by this, which is if you look at this geometrically, it's the total number of edges, these 5 edges here, the total number of edges, and also the diagonals in this n plus 1 gon. In this case, it's a pentagon. N plus 1 is 5. So again, the total number of handshakes equals the total number of edges and diagonals in this pentagon, this 5-sided polygon. In this case, n plus 1 is 5. Each of the 5 people has shaken hands with 4 other people. But we don't double count the handshakes. We only count the handshake between 3 and 4 and 4 and 3 as one handshake, for example. So right off the bat, my conjecture, my guess, is that the expression for method 1, the sum of the first n positive integers, 1 plus 2 plus 3 plus yada, yada, yada plus n, I conjecture that this equals the fraction n times the quantity n plus 1 all over 2. For method 3, I'll show you a second way how we could have gotten this expression. Method number 3, imagine the n plus 1 people in the room. Each pair of people shake hands. Now, how many ways are there to choose 2 people out of n plus 1 to shake hands? Basically, how many pairs of people are there in this group of 5? How many pairs of people are there? And each pair of people has shaken hands. Okay, well, we have 1 and 2, 1 and 3, we have 3 and 4, and so forth. N plus 1 choose 2. That's the number of pairs among the n plus 1 people. How many ways are there to choose 2 people out of n plus 1? You can also write this as n plus 1 C2, the number of combinations of n plus 1 people taken 2 at a time. And I claim that this equals that fraction that we saw from method 2. The same fraction as this fraction we got from the polygon approach, the total number of edges and diagonals. Now, this isn't as obvious, but look at my notes. Okay, it's explained in my notes. N plus 1 choose 2. If you write this in factorial form, it's n plus 1 factorial all over 2 factorial times, this turns out to be n minus 1 factorial. if you have n plus 1 runners in a race, 2 of them win, the other n minus 1 lose. Now, how do you simplify this factorial expression? This is great for the homework. Take the bigger factorial and start unraveling it until you get a great cancellation. N plus 1 all factorial, let's do the countdown. What are the factors here? We start with n plus 1. We count down. We then have n. And then we have n minus 1, yada, 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 all the way down to 1. But the product of all those will be n minus 1 all factorial, which cancels out, divides out completely with this guy down here. We get 1s here. So we're left with this simple expression, which we can, where we can switch around on top. Multiplication is commutative. We have n times the quantity n plus 1 all over 2 by working out this algebra very deeply. Same as what we got over here.
Okay, now hold on. Let me pause. Did you get that? Because that's the kind of thing you're going to see on the homework. And that's the kind of thing you're going to see in Calc 2. Simplifying this kind of factorial expression in something like n. You're going to see that on the homework. Any questions about that? All right. You might want to take a look at it.
Times the quantity n plus 1 all over 2 by working out this algebra very deeply. Same as what we got over here. In any case, my claim, my conjecture, is that this is true for all positive integers n. The sum of the first n positive integers, 1 plus 2 plus 3 plus yada, yada, yada plus n, equals the fraction n times the quantity n plus 1 all over 2. And we're going to use mathematical induction as a means of proving this conjecture, this guess. Mathematical induction is used to prove conjectures or guesses, statements that we believe to be true, but are as yet unproven, even though you may have been convinced by my arguments. Now, unfortunately, the method itself will not give you this formula over here, okay? You have to arrive at it from your reasoning, like what we did with these 3 methods. For example, method 1 and method 2, or method 1 and method 3. Remember, method 1, remember that method 1 gave us this, the sum of the first n positive integers, and then both method 2 over here gave us that formula, that fraction, and method 3 also gave us that fraction after some algebra, after a bunch of algebra. So we can conjecture this based on equating our expressions from method 1 and method 3, or from method 1 and method 2. Induction is then used to verify or prove our guess, our conjecture, and then we have a bona fide theorem. By the way, a fourth way you could have done this. If you remember arithmetic series, this is the nth partial sum of a basic arithmetic series. The formula for the nth partial sum can be found by using a formula we saw in section 9.2, and we arrive at this once again. Although we technically skipped that as we went through 9.2, that was optional. So really 4 ways. There were 4 ways, at least, of figuring out or guessing this. And then finally, in our next videos, we're going to prove this using mathematical induction.
And by the way, this is the core of combinatorial thinking, what Art Benjamin does, that one TED talker. It's like different ways of counting the same thing, different ways of counting the answer to the same question, right? And you're equating these things, like the sum here and that formula. All right, again, questions in chat. Okay, because I'm sure there'll be questions along the way, and I'll email out a Khan Academy video, which will have a second opinion on all this. All right. Let's go on. Remember, we did this for the first 100 integers. Remember the sum of the first 100 integers? I showed you some videos on that.
Hi, everyone. So the bottom line is that you need to be able to prove this conjecture, that the following is true for all positive integers n. That is for all n in the set of positive integers, z plus. P sub n, the statement P sub n, this is like a proposition, which states that the sum of the first n positive integers, 1 plus 2 plus 3 plus yada plus n, equals this fraction, n times the quantity n plus 1 all over 2, where the left-hand side is not in closed form, but the right-hand side is a closed form formula, which was which was obtained from combinatorial interpretations from methods 2 and 3. Now, bear in mind that we're trying to prove here infinitely many statements. How do you prove infinitely many statements? Because remember, a piece of n gives us a different statement, technically, for each different positive integer n. So we want to prove infinitely many statements corresponding to the infinitely many positive integer values of n. How do you do that? Proving infinitely many statements? And when do you do it? Well, in quite a bit in higher math. Induction is commonly used in discrete math and in linear algebra, especially. For example, what if you want to prove something, a property is true for all square n by n matrices? Well, you want to show that's true for 1 by 1 matrices, 2 by 2, 3 by 3, and so on, 100 by 100, and so on. So how in the world do you prove this statement if you're considering all these infinitely many cases? Also, if you want to prove a property for determinants of square matrices of various sizes. Also, induction is used in continuous mathematics. For example, in calculus, induction is used to prove integration formulas involving powers of or products of powers of trig functions. So for example, how do you integrate sine to the nth of x for high positive integer values of n? Induction is used as a method of proof in higher math. Now, what's the key idea behind induction? Well, you can think of it as climbing a ladder, as we mentioned before, all right? We can also think of it in terms of a domino image or analogy. So imagine this line of dominoes, a line, kind of an array almost, of infinitely many dominoes. When are we guaranteed that each domino will eventually fall? Well, I hope you agree that eventually each domino will fall if we have the following holding true. If it's true that the first domino falls, and that corresponds to the basis step, so that means that this first domino gets tipped over, right? And then the fall of one domino guarantees the fall of the next domino. And this corresponds to what we call the inductive step. So if one domino falls, then we're guaranteed that the next domino will fall. If one falls, then two falls. If two falls, then three falls. If three falls, then four falls, and so forth. If a domino falls, it means that basically this statement is true for the corresponding value of n. So if one falls, that means that piece of one is true. If two falls, that means that piece of two is true. If three falls, piece of three is true, and so forth. Okay. By piece of three falling, we mean that this statement is true in the case of n equals 3, in which case we don't worry about this piece here. We're saying that 1 plus 2 plus 3 equals what you get when you plug in n equals 3. Bear in mind that even though this left-hand expression may seem to only make sense for reasonably large values of n, we assume that if n is small, it compresses. So if n is 1, then the whole left-hand side compresses down to just 1. So the expression compresses as necessary. So in order for each domino to eventually fall, we need the first domino to fall. And if one domino falls, then we have to be guaranteed that the next domino will fall. Now, if you agree that both of these happen, then you agree that each domino will fall eventually down the line. Now, of course, we need the first domino to fall. It's nice if these dominoes are stacked like this, but if the first domino is not falling, these dominoes might just be staying there. I mean, how are they going to fall? Am I going to yell at the dominoes, fall? Well, I don't know, maybe nowadays with my breath it might work, but, I think it would help for the first domino to fall, okay? Now, that's not enough. I mean, if the first domino falls, right, that's not enough. Let's say this domino falls, domino 1, okay? It could fall and then poop. It just kind of lies down there and it doesn't affect any of these other dominoes. So if domino 1 falls, it doesn't help much if we're not guaranteed that the next domino will fall, and then the next domino, and so forth. If these dominoes are too spread apart, then it doesn't matter very much that the first domino falls because you're not starting the chain reaction. We need the dominoes to be kind of close together to be able to see the chain reaction execute. That's basically the inductive step, the guarantee that if one domino falls, we're guaranteed that the next one will fall. So that's the idea of the domino image or analogy. The actual proof, which you need to know how to do, we're going to talk about in detail next.
Okay, now, those are the ideas. Any questions about the ideas? We're going to execute this in the next video. Questions. Questions. So this is all a leap of faith. Questions. It is mathematically legitimate, though.
All right, folks, let's prove this conjecture. We're going to prove this statement for all positive integer values of n. First of all, don't forget the basis step. We have to verify that domino 1 falls. We can't just yell fall, right? Even with my breath. We need to show that domino 1 falls. We need to show that p sub 1 is true. Verify that proposition or statement p sub 1 is true. That is, show that this is true, verify it's true in the case where n equals 1. So this statement, what is this statement in the case where n equals 1? All right, well, and then in red, I'll emphasize the parts you need to write. All right, well, the left-hand side, when n is 1, this all compresses down to just the 1 over here. The sum of the first one positive integer is just 1. And then you plug in n equals 1 on the right-hand side, 1 times the quantity 1 plus 1 all over 2. And then you verify that 1 equals 1. So you should write this and this. Okay, and of course, 1 equals 1 is a true statement. This demonstrates that p sub 1 is true because we've shown that p sub 1 is equivalent to the true statement 1 equals 1. The basis step. You must remember the basis step. A lot of students forget it. But remember, the first domino has to fall. Otherwise, the dominoes are just standing there. Remember this. Don't lose easy points. So that wasn't the hard part. The hard part is the inductive step. By the way, let's say that we wanted to prove a statement p sub n for all integers n such that n is greater than or equal to 7, let's say. Then we would use p sub 7 as our basis step. In our stamps problem, I guess we start with p sub 6, 6 cents, right? So it's not always p sub 1 corresponding to the basis step, but it often is. Okay, now the inductive step. The inductive step. Now this is a step where we verify that whenever a domino falls, it will also knock over the next domino down. If 1 falls, then 2 falls. If 2 falls, then 3 falls, and so forth. A domino falling means that the corresponding proposition, p sub n, whatever n is here, is a true statement. Falling means true statement. All right. Let k be a fixed positive integer, which we might write like this in shorthand. Some books use n, similar to the way we used n up here, although n here kind of varies in a sense. So I think it's more proper to use k, but if you use n, that's fine also, just be consistent. But we're assuming for now that k is a fixed positive integer. It's a constant as we make these arguments. First off, assume that p sub k is true. And this assumption, this very important assumption, is called the inductive hypothesis, which I might abbreviate as IH. Okay, what this means is that we're going to assume that domino k falls. Okay. We're going to assume that domino k falls. Assume that the kth domino has fallen. Now, you should state what p sub k is. What is the statement P sub k? Well, basically, you're rewriting the statement P sub n, where you're replacing n with k. Again, some books just run with n and just copy this down. Okay, I think it's better to assume that k is a fixed positive integer for our argument here. Assume that P sub k is true, okay, which means this. P sub k is this, where we replace the P sub n statement with P sub k. We substitute n equals k. So we assume this. Now, we have to show that the proposition or statement P sub k plus 1 is then true. So given that we're assuming that domino k has fallen, we need to show that domino k plus 1 will also fall. So assuming that domino k falls, we're going to show that k plus 1 will also fall, presumably as a consequence of domino k falling. Incidentally, this here is an example of weak induction. In strong induction, we assume that all previous dominoes down to 1 have all fallen. That's for strong induction. For weak induction, we just need the previous domino to fall and showing that the next domino will then fall. All right. So we need to show that P sub k plus 1 is then true. What is P sub k plus 1? Well, we take the original statement for P sub n, we substitute n equals k plus 1. So k plus 1 is the last positive integer to be added in. We replace n with k plus 1 in the right side as well. All right, so here's P sub k plus 1. It might help to have a duplicate copy of this. There we go, duplicate. All right. So let's go to the statement. Okay. Over here, all right. So here's P sub n in general. Okay, and we're substituting n with k plus 1. So here we have the sum of the first k plus 1 positive integers, 1 plus 2 plus 3 plus yada, 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 plus, and then k plus 1 equals, all right, this is kind of tricky. Every time we see an n, we substitute it with the quantity k plus 1. So substitute n with k plus 1. Substitute n with k plus 1. Now n plus 1 becomes k plus 1 all plus 1. Well, that becomes k plus 2. So we can simplify this right-hand side a little bit right now. Okay, so we get k plus, the quantity k plus 1 times the quantity k plus 2 all over 2. Okay. So like in a trig verification problem, we can think of this now as our new target. The target is going to be this over here. Let's do it. Let's show this. But we're going to need the inductive hypothesis, this thing here, as a crucial part of proving that this is now going to be true. How do we do it? All right, let's copy the left-hand side. Okay, this is the thing we have to show now, all right? Let's copy the left-hand side, the sum of the first k plus 1 positive integers. Now, it's going to be helpful. Let's assume that k is big enough. It's going to be helpful to write the second to last term over here, the second to last integer over here. So we have the sum of the first k positive integers plus k plus 1 over here. And now we can apply the inductive hypothesis to all this. 1 plus 2 plus 3 plus all the way up to k. Because according to the IH, the inductive hypothesis, we're assuming that this sum is equal to this fraction, k times the quantity k plus 1 all over 2. So we can do a substitution. We have the right to substitute all of this with this nice fraction over here, k times the quantity k plus 1 all over 2, which is a nice closed form formula. We no longer have the ... ellipsis stuff anymore. This is now a closed form formula. In fact, when you look at the sum here, this fraction plus this quantity over here, we have a closed form expression for this over here. Okay, now we need to hit the target. The target is this, the quantity k plus 1 times the quantity k plus 2 all over 2. Right there. Okay, so now let's add these two rational expressions. Right now this is over 1, okay? But I want to have a 2 in the denominator, so I'm going to multiply this fraction by 2 over 2. I'm multiplying by 1 creatively. So then we get this fraction over here plus 2 times the quantity k plus 1 all over 2. We now have a common denominator. We can add the fractions, keep the common denominator, and add the numerators. K times the quantity k plus 1 plus 2 times the quantity k plus 1. And then from factoring, what can we factor out in the top here? We can factor out k plus 1 on either the right side or the left side. In the end, we need to have k plus 1 on the left so that we hit the formula over here verbatim. Now, visually, it looks like we should factor k plus 1 out to the right. That's fine, but eventually switch these. Eventually, we need k plus 1 on the left to hit the target verbatim, right on the dot. The other factor, once we factor out k plus 1, the other factor is k plus 2 over here, right? I'll put that in green, right? Remember, we have the k times this plus 2 times that. We have k plus 2. The idea is that we're factoring in such a way that we're reversing the distributive property, right? Because if you distribute k times this thing, right, plus 2 times this thing, the k plus 1. Again, if necessary, switch the factors. We hit the target verbatim on the dot. And I should put all of this in red. You should write all the, well, you don't have to write this. Well, actually, you know, that's a good idea, actually. Mention the IH, like maybe by the IH, at least write by the IH, by the inductive hypothesis. You should write all of this down. Bear in mind, if you skip, say, this step here, it's okay if you then write this step. And I'll believe you if you go from here to here, for example. Okay. So you may not have to write every single step, but it's a pretty good idea to write all these steps. You would skip from here to here, of course. Okay. You would factor out k plus 1 to the left. Okay. And really, we're done. We're done. Remember that all this applies even if k is relatively small, then this thing compresses as necessary. Okay. Conclusion. Because we've done it. We've shown that from the basis step, domino 1 falls, right? From the basis step, domino 1 falls. And from the inductive step, if domino k falls, then domino k plus 1 also falls. So we've done it. We can now conclude that P sub n, which is the original statement up here, okay, P sub n, this proposition on n, is true for all positive integers n. The 3 dots sometimes indicates a conclusion, like there, it says therefore, therefore. P sub n, this proposition is true for all positive integers n. Sometimes QED indicates end of proof. It's Latin. It's a Latin acronym. That which was to have been proven. It's nice to put a final flourish on things. We've done it. we have proven infinitely many statements at once. We have proven P sub n for all positive integers n. We have proven infinitely many statements. Very impressive. And then you can apply this formula, right? So now you can you can find the sum of the first 1,000 positive integers very quickly, the sum of the first 5,000 positive integers very quickly by using this handy dandy closed form formula. It's pretty nice. There are also other formulas for sums of powers, the sums of the squares of the first n positive integers, and so on and so forth. Finally, if you like the stamps problem at the outset, if you wish, you can use induction to prove that every amount of postage greater than or equal to 12 cents can be formed by just using 4 and 5 cent stamps. Going back to the stamps problem we introduced this section with. Okay, proof by mathematical induction.
All right. Now, I know it may take time for you to think about that. And basically, the homework assignment is that same proof. So it's a matter of the key homework assignment from 9.4. So basically, it's a matter of reiterating that proof and understanding it. Okay. So I know it may take some time. You may need to get back to this and also send out the Khan Academy video. Now, in section 9.5, we're going to talk about these powers of binomials. And I want to go back to these memes I had before. Okay, I've shown this a million times, right? What's the square of a plus b? Don't make teacher mad, okay? It's not a squared plus b squared, right? Okay, don't miss the middle. Don't miss the 2ab, otherwise teacher gets mad. Hopefully I won't get that mad. And that's not blood, that's a cloud. All right, now here's a really cool thing, all right? Here's a plus b all to the first, it's just a plus b. It's like these Lego pieces almost, or these building blocks. The square of a plus b, if this is a and that's b, a squared, it's not just a squared plus b squared, you also have these two strips over here. ap plus ab, that's 2ab, right? The area of the square is the sum of these four little areas, right? But it's not just red plus blue, you also need the purple pieces. The cube of a plus b is like a big Rubik's cube, right? And you have all these different pieces. It's not a cube plus b cube, you have these other pieces. But there is a nice pattern to these terms. The fourth power, you have even more terms, but there is a pattern here. Take a look at this. In fact, I'll have you look at it for a few moments. What are the patterns as we go from a to the fourth to b to the fourth? So think about that. And by the way, this is called a tesseract, like from A Wrinkle in Time. It's like we're taking a cube and we're sliding it, or we're looking at it over time. So this is kind of freaky looking. It's a four-dimensional figure. All right. The binomial theorem. How do you expand a plus b all to a non-negative integer?
Hi, everyone. Let's do section 9.5 on the binomial theorem, which can itself be proven by induction, 9.4. And actually, you're going to do this in calculus as well, as we'll see. But this is in and of itself an interesting algebra problem. So how do we expand a plus b all to the n, where n is a non-negative integer? And in fact, I claim that by the end of this section, you're going to be able to work out a plus b all to the 10th with the help of a scientific calculator maybe, and you can do it within a couple minutes, accurately. All right, in the beginning, a plus b all to the 0, assuming that a plus b is not 0 itself. A plus b all to the 0 is 1. Or remember, 2 to the 0 is 1, 3 to the 0 is 1. Likewise, this thing to the 0 is 1. A plus b all to the first is just a plus b. A horse is a horse. The square of a plus b, folks, it's not just a squared plus b squared. Please remember this middle term here. Don't be like these bad kids. Remember, don't be like these bad kids here in the lower left panel. All right. The square of a plus b is a squared plus what? Plus 2ab, plus twice the product of the two terms, plus the b squared. Now back in your Algebra 1 class, to find the cube of a plus b, you could take basically the square of a plus b, which was this thing over here, and multiply by a plus b. and distribute like crazy. So what you might do is take the square of a plus b, substitute in, well, take the square of a plus b, substitute it by this over here, all right? And then multiply by a plus b, distribute, combine like terms, and you get this. And by the way, see if you can figure out a pattern here. We're going to talk about this. A cubed plus 3a squared b plus 3ab squared plus b cubed. Now, of course, an Algebra 1 student would take some time to get to there, right? And at this time, you might need some time to get to here, but try to see a pattern, especially with the variable parts. Try to see a pattern. We'll talk about this. Now, in an Algebra 1 class, if you're asked to expand out the 10th power of a plus b, oh yuck, that would take you quite a long time. But again, I claim to you that maybe with the help of a scientific calculator, you'll be able to do this within maybe a couple minutes accurately by the time we're done with this section. Oh, now by the way, there are some geometric representations for these. I believe this came from the art of mathematics. So we can imagine the first power, the second power, the third power, even the fourth power as representing a combination of pieces here. So the square, a plus b all to the first, you're just adding lengths of line segments. The square of a plus b is like you're adding areas, right? The square of a plus b is not just a squared plus b squared. You also need these purple pieces over here, right? The 2ab pieces here. The cube of a plus b, you can interpret in terms of volumes of these pieces here. The volume of the cube equals the sum of the volumes of these various pieces here. This is called a tesseract. If you've ever read A Wrinkle in Time, it's like moving a cube through time, maybe. maybe moving a cube through time, or just physically moving a cube, kind of thinking of it that way, all right? 4 dimensions. All right. Anyway, look for the patterns. Let's go back to the cube of a plus b. Look at the variable parts of the terms. You can ignore the 3's for now. Although it's no coincidence that 3 is the exponent over here and here. Now, if we expand out the cube of a plus b, it's not surprising that we start with a cubed, usually, and we end with b cubed. Bearing in mind that you have the right to reverse the order, right? We have commutativity here. You can switch a and b, and there's a symmetry that works here between a and b. But in any case, we normally start with a cubed, the cube of the first term, and we end with b cubed, the cube of the second term here. But as we move from term to term, look at the variable parts. What happens to the exponents on a? What happens to the exponents on b? Well, over here, it's like we have an invisible b to the 0, which is 1, right? We have an invisible 1 here for b to the first. Over here, we have an invisible a to the 0. I guess I should put that here. We have an invisible a to the 0 and an invisible 1 over here, right? So what's happening to the exponents on a? Well, we're going from a to the third to a to the second to a to the first to a to the 0. And maybe I should put these pieces in blue. A to the first here, a to the 0 over here. A to the 0 is 1. And let's assume for now a and b are not 0. Remember, 0 to the 0 is weird. So the exponent on a is going down 1 by 1 as we go from term to term, the way we normally write this. What about the exponent on b? Well, we start with b to the 0. We then go to b to the first, then b to the second, then b to the third. So basically, at each step, as we move from term to term, the exponent on a goes down by 1 with each new term, and the exponent on b goes up 1 with each new term. And notice also that the degree of each term is 3. Okay. Because remember, to get the degree of a term such as these, you add the exponents on A and B. So here, of course, A cubed has degree 3. That's no problem. But the A squared B term here, this also has degree 3 because the degree on A, the exponent on A is 2. The exponent on B is 1. The degree here is 3. 1 plus 2 is 3. Over here, B cubed has degree 3. So each of these terms has degree equal to the exponent over here. All right. Each term has degree 3. So in general, when we consider a plus b all to the n, where n is a whole number, a non-negative integer, we start with a to the n, we end with b to the n, and we end up with n plus 1 terms after we combine all like terms. Notice here that when we had the cube of a plus b, we had 4 terms, right? For example, the exponent on b goes from 0 up to 3. For emphasis, I'll emphasize the exponents on b. B to the 0, b to the first, b to the second, and b to the third, right? We have 4 terms here, not 3. So we have n plus 1 terms, all right? The number of terms is the exponent here, plus 1. Now, what about the coefficients, all right? So we've talked about how to get these variable parts here. And by the way, I'll give you a moment to write down the variable parts for a plus b all to the 4th. So if you were to do a plus b all to the 4th, what would be the variable parts, ignoring the coefficients for now? I'll give you 15 seconds. Okay, so we'll check on that in just a moment. What about the coefficients? Like, how do we know the coefficients are 1, 3, 3, 1 here? I'm going to erase all this for now. How do we know the coefficients are going to be 1, 3, 3, 1? How do we know these are going to be the coefficients? It's from something magical, something really amazing in math. They're given by Pascal's triangle, named after Blaise Pascal. Here are the ingredients. Now, you might remember Pascal's triangle from your old algebra days. How do you construct Pascal's triangle? You start with a tent of ones, and you start with row 0 on top, by the way. And for every other entry in Pascal's triangle, all right, basically the way to look at it is that every time you have 2 consecutive entries, the sum of the 2 entries will be the entry right below. Every other entry is like the child, is the sum of the 2 entries immediately above. So for example, well, this is Pascal's triangle, in fact. At the top, you start with row number 0. Here, n equals 0, right? The row number is n. We start with n equals 0 on top. There's just a 1 there. For n equals 1, we have a pair of 1s. For n equals 2, we keep building this tent of 1s, but there's an entry in here. Now, how do we get the 2 here? We get the 2 by taking the sum of the 2 parents. Every time you have 2 consecutive numbers in Pascal's triangle, they give birth to their sum. 1 plus 1 is 2. Try to figure out row number 3. It will ring a bell. For row number 3, again, we have a tent of 1s. We have a 1 on the left edge, a 1 on the right edge, right? 1 plus 2 is 3. And also, 2 plus 1 is 3 over here. Every time we have a pair of consecutive numbers in Pascal's triangle, they give birth to their sum. And we place that number below and in the middle horizontally. Now notice here, for row number 3, we have 4 terms. For row number 2, we had 3 terms, okay? Or numbers. So notice that for row number n, we have n plus 1 numbers in Pascal's triangle in that row. That corresponds to the fact that, remember in the expansion, if you're expanding a plus b all to the n, you have n plus 1 terms over here. For example, for a plus b all to the third, we have 4 terms over here. All right. For row number 4, we go 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then the 1 over here. And we could go on and on and on. For a plus b all to the 10th, you would go to row number 10, which is the 11th row in the triangle. Notice we have symmetry. We have symmetry about this central axis. That explains why. Over here, for example, see, it's okay if you switch A and B. There's a symmetry. You can go either this way or this way. All right, 1, 3, 3, 1, you have symmetry among the coefficients. All right, so row n gives the coefficients for a plus b all to the n. The square of a plus b, the coefficients are 1, 2, 1. Look over here, 1, 2, 1. Okay, these bad kids should have known that. It's not 1, 0, 1, it's 1, 2, 1. All right, now the cube of a plus b, all right? We had the variable parts. Now we know the coefficients are 1, then 3, then 3, then 1. Now, when I asked you about a plus b all to the 4th, you should have gotten the variable parts, okay? Now attach the coefficients. I'll give you a moment to do that. Give you 10 seconds to attach the coefficients. All right, here's a plus b all to the 4th. We typically start with a to the 4th and we end with b to the 4th. The variable parts. Okay, as we go from term to term, the exponent on a drops by 1 each time. A to the 4th, then a to the 3rd, then a to the 2nd, then a to the 1st, then a to the 0, right? The exponent on b increases by 1. So we go from b to the 0, to b to the 1st, to b to the 2nd, to b to the 3rd, to b to the 4th. By the way, it's very easy to make a mistake. For example, you might get confused and you might end up increasing both exponents or decreasing both exponents. One way to do a quick check, make sure that the degree of each term is n, the exponent over on the left. In this case, the degree would be 4, right? Degree is 4 here. Here, 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. And the 4 over here. Each term here has degree 4 if the 4 is over here. That's a good check because a lot of people make a mistake. For example, they might go from 3 and 1 to 4 and 2, for example, and that would be a mistake. You can check the degree of each term to help make sure you don't make those kinds of mistakes. Because you're going down for one variable and up for the other variable, it gets confusing. And so on and so forth. Now, at this point, you should believe me that you should be able to do a plus b all to the 10th with the help of a scientific calculator within a couple minutes. The variable parts, it follows a similar pattern. You're going to have 11 terms. Now, Pascal's triangle, that might take some time to write out, right? Bear in mind, though, you don't have to go through the whole triangle because it does turn out that for row n, and entry R, where you start with R equals 0 over here, and you end with R equals n, or R equals 4, in this case, over here. The entries here correspond to binomial coefficients, NCR, these combination numbers. So 52C5 is going to be way down there, the 2.6 million or so. That's going to be way down there in row number 52, the 53rd row in the triangle, and in R equals 5, that's in the 6th position because you start with R equals 0. R equals 5, that's going to be in the 6th position from the left, and that's going to be the 2.6 million or so, the number of ways to get 5 cards out of 52. This here. Pascal's triangle is a triangle of binomial coefficients, these NCR values that we mentioned before in section 9.6. All right. And it explains the symmetry also. Okay, now you can expand general
But
power
I almost forgot to
in section
mention.
9.6.
All
right. And it explains the symmetry also.
Yeah. So I noticed that, yeah, don't forget you attach the coefficients 1, 4, 6, 4, 1. That's pretty evident, but I technically forgot to say that. You attach the coefficients from Pascal's triangle here 1, 4, 6, 4, 1. Okay, I technically forgot to mention that.
Okay, now you can expand general powers. So for example, if you have the cube of 3x minus y, you might want to do a substitution and then use the binomial theorem. All right, so we have the cube of 3x minus y. You could let a be 3x, let b be the opposite of y, because we like to have the sum in there, right? So 3x minus y is 3x plus the opposite of y, all right? You cube all this, okay, do the substitution, the cube of a plus b, they should look familiar from before. Then sub back using parentheses. I'll put this in red. A lot of people forget the parentheses. Replace a with 3x, replace b with the opposite of y in parentheses. Simplify. All right. And we end up with this over here. Again, put grouping symbols where necessary. Remember, if you have a cube deal here, in a typical situation, you end up with 4 terms over here. So you can use the binomial theorem to work out these kinds of general powers, if you wish. Finally, where do we see these things in calculus? Let's say, for example, f of x equals x cubed. You might want to find the difference quotient, and in calculus, you may have to, right? Rise over run, f of x plus h minus f of x all over h. Remember? Okay. You have 2 points on the graph of f. You want to know the slope of the secant line, right? Here's x plus h. Here are the corresponding function values, the y coordinates. So here's f of x, which is the y coordinate over here, and f of x plus h. Which is the y coordinate over here. All right, the slope of the secant line. And what is f of x plus h? Be careful. It's not, don't engage in wishful thinking. It's not x cubed plus h. Trust me. What is f of x plus h? When you see this, think what S word? Think substitution. You're going to substitute x with x plus h. Substitute x with x plus h. So you get here not x cubed plus h, but the cube of x plus h. You replace the x, it's like a kernel of popcorn, it explodes, and you get x plus h as the base. You're cubing x plus h now. Hey, how do you cube x plus h? The good old binomial theorem. Okay, it looks very similar to what we saw before, except you have an x and an h instead of an a and a b. Proceed. If you take the limit as h, the bottom approaches 0, as the run approaches 0, you're going to get the slope of the tangent line. The slope of the tangent line, and that's given by the derivative, which is 3x squared. That's the slope formula. For various values of x, well, remember the graph of y equals x cubed looks like a snake, like so, right? This is the slope formula. The slope at x equals 0 is, plug in 0, you get 0. The slope at the point where x equals 1, the slope of the tangent line, is going to be 3. That's the slope of the tangent line at the point where x equals 1. All right, you're going to see this stuff, the binomial theorem, when you're working out the derivatives of polynomial functions using the limit definition of derivatives, which employs difference quotients. Now, bear in mind, you might be going, wait a minute. It's like man overboard. 3 men over here. Okay, man number 3 drops down. 2 men left on board. Does that extend? Yes, it does. It's a shortcut. What's the derivative of x to the 4th? Take a wild guess. What's the derivative of x to the 4th? It's going to be 4x cubed. That's a shortcut, but you should be able to prove it. Now I'm going to show you some really beautiful and brilliant properties of Pascal's triangle, which is really one of the most remarkable things in math.
We'll say that to the end of the class, actually. We'll get to the business with ellipses after the break. We have a much-deserved break, all right? Return at 8:32. I have 8:21 now. So come back at 8:32. Remember to mute. All right. And I'll see you at 8:32. So we're going to my more handwritten notes in chapter 10.
Hi, everyone. Let's do chapter 10 on conic sections, polar coordinates, and polar curves. Most of these notes are handwritten, so these lectures will help to organize them. Let's get right to it. Conic sections include circles, which we know very well from before, section 0.13, ellipses, which we're now going to do, which are ovals, kind of like warp circles almost. And then later on, we're going to talk about hyperbolas and parabolas. Now, parabolas we saw back in chapter 2. We'll talk a little bit more about them in chapter 10, just a little bit. But in chapter 10, I really want you to be able to analyze ellipses very carefully. Again, ellipses are ovals, basically. Special types of ovals. All ellipses are ovals, but not all ovals are ellipses, all right? This is not an ellipse. It's too squarish. All right, let's get right to it. 10.3 on ellipses. And we're going to start with the key anatomy, notation, and mechanics for ellipses. And we'll talk about more features later on. The locus definition of an ellipse. Well, what do we mean by a locus definition? That's more of a set theory or a geometric definition of a geometric figure. So for example, what's the locus definition of a circle? Well, for a circle, you have a fixed point called the center, and a circle consists of all points that are equidistant from that fixed point, that distance being the radius. And you don't need x coordinates or y coordinates to talk about that. But what's the locus definition of an ellipse? Now, an ellipse does not have a single radius, as you see, right? It does have a center. Okay, we do still have a center here, but we don't have a single radius. The points on the ellipse are various distances away from the center. Now, instead of focusing on the center, we're going to focus on two other fixed points called the foci, which is the plural of focus. Foci is the plural of focus. So we have one focus over here, f sub 1, one focus over here, f sub 2. You can use different notations. Now here's the idea. Again, for a circle, the idea was that every point on the circle had the same distance from this fixed center. Over here, it's a bit different. If you take a point on the ellipse, you can consider the sum of the distances between this point and each focus. Basically, this length here plus this length over here. And the idea is that the ellipse, this ellipse here, consists of all points whose sum of distances from the two foci will stay constant. The sum stays constant. So for example, here, a d sub 1 plus d sub 2, the point here has sum of distances from the foci, same as for this point over here. Okay, for this point P2, d sub 3 plus d sub 4, the sum in purple is equal to the sum in red. This corresponds to the way that the ellipse is constructed, and I've shown a video on this, all right? Imagine that you have two thumbtacks that we're about to attach to the ends of a taut string, okay? So you have this string here that's bent over at the ellipse, right? And the ends of the string are tied down by thumbtacks, right? Now, your pen or pencil or marker pushes out on the string until it's taut. There's no slack in here, right? You move the pencil or pen around, and as you do that, you form an ellipse. This makes sense because since the string is being held taut, this sum of distances from the points on the ellipse to the two foci will stay the same because the string maintains its length. The total length of the string stays the same. All right, let's talk more about anatomy, terminology, right? The anatomy of an ellipse. Okay. Just like for a circle, the ellipse does have a center. And the center is the intersection between the major axis over here and the minor axis over here. In a way, you can think of the major axis as the longest diameter in an ellipse. And the minor axis is the shortest diameter in an ellipse of all line segments or chords that go through the center. So we don't count things like that. Okay, so you can think of the major axis as like the longest diameter, the minor axis as like the shortest diameter, in a way. And they both have to go through the center. They intersect at the center. The two foci, F and F prime, we've discussed before. These are the two foci that helped us draw the ellipse in the first place. The two endpoints of the major axis are called vertices. An ellipse has two vertices. A parabola had one vertex. A circle had no vertices, really. A parabola has one vertex, right, over here. An ellipse has two vertices, and they are at the endpoints of the major axis. They're the 2 points on the ellipse that are furthest away from each other. Again, they're at the endpoints of the major axis. The endpoints of the minor axis don't have great names to them, but they're often good to graph with precision. Again, the minor axis extends from this point to this point. All right. Now this, by the way, this particular ellipse is called a horizontal ellipse. Later on, I'll call it an x-long ellipse in the sense that it's elongated in the horizontal or x direction. All right. Notation. So look at the center here. The distance between the center and each vertex, I'll call the vertices V and V prime. In red here, I'll call the vertices V and V prime. The prime here does not mean derivative. It's just a piece of notation. So A is the distance between the center and either vertex. B is the distance between the center and either endpoint of the minor axis. So the major axis has total length 2A. The minor axis, which I'll put in green, the minor axis has total length 2B. To be or not to be, it's 2B. Now that's for a, now for a horizontal ellipse, it looks like that. For a vertical ellipse, again, this is for a horizontal ellipse over here. For a vertical ellipse, it looks more like this. Okay. One moment.
I kept forgetting how to recolor text. It's that A thing.
Okay, one moment. For a vertical ellipse, okay. Vertical ellipse or Y-long ellipse. Okay, now for a vertical ellipse, okay, the center is over here, all right? Center's over here. Major axis is vertical. So, you know, for a horizontal ellipse, the major axis is horizontal. For a vertical ellipse, the major axis is vertical. Okay, major axis is vertical. The vertices are at the endpoints of the major axis. Let's say V here and V prime over here, or vice versa. Right? The foci, by the way, would lie on the major axis. in red here, and in red here. So the major axis will have 5 key points: the center, the 2 foci, and the vertices. Over here, see, we have the center, the 2 foci, and the 2 vertices. 5 key points on the major axis. So over here, we're going to have 5 key points on the major axis. Again, the length is 2a, just like before. For the minor axis, the length is 2b, just like before. All right, but just in different orientations. Now, the major axis is longer than the minor axis. They cannot be equal because otherwise we'd have a what? We'd have a circle, right? The major axis has to be longer. So that means that A has to be bigger than B. That is, B is less than A. And they both have to be positive. So we'll assume that 0 is less than B, which in turn is less than A. In other words, A is greater than B, and both are positive. If A were to equal B, again, we'd have a circle, but a circle is not technically an ellipse. Sometimes when you're thinking about the theory and the way these shapes work, it's sometimes convenient to think of a circle as like a degenerate ellipse, but a circle is not technically considered to be an ellipse, although it's sometimes convenient to think of it as a degenerate ellipse. Okay. Now, what's C? We have A and B. What's C? C is going to be the distance between the center and either focus. So we have C over here and C over here. Remember, A is the distance between the center and either vertex. So this is going to be A over here. This is going to be A over here. This distance between the center and either vertex. You can see here C is less than A. Okay, C is going to be less than A. And we know that B is less than A also. So both B and C, we know, are going to be less than A. So how do we compute C? It turns out, and I'll show you later on why this works, maybe next time, C squared equals A squared minus B squared. Look at that. Now, don't confuse this with the Pythagorean theorem. The Pythagorean theorem said C squared equals A squared plus B squared. Now, the Pythagorean theorem is involved here, but the way that the triangle is labeled, the right triangle is labeled, it goes C squared equals A squared minus B squared. I'll show you why it's a minus later on. This does make sense because remember, we just said that C was less than A, right? The distance between the center and either focus, C, is less than the distance between the center and either vertex. In other words, the foci are closer to the center than the vertices are. C is less than A, which makes sense that here, right? It makes sense that A squared is going to be less than C squared, okay? Because C squared is going to be A squared minus this positive value here. So this reflects the fact that C is less than A, the fact that that's a minus sign. All right. So again, C is the distance between the...
I made a mistake that C squared is less than A squared. C squared is less than A squared. So C is less than A.
The center and either focus. That's the case for a horizontal ellipse or a vertical ellipse. In this class, we're not going to do 45-degree ellipses, although you do see those in Calculus 2, Math 151, rotating conic sections. In this class, we might rotate them like 90 degrees or 180 degrees, but not 45 degrees, not in our class. Next up, we're going to talk about standard forms for the equations of ellipses. Next time.
So where are X and Y? They're coming up next time. Like, how do you graph these things on Desmos? Questions before we go on. And after this, you'll be able to do all the homework on chapter 9 and the 10.3 problems. All right, questions.
Hi, everyone. Let's talk about standard forms for equations of ellipses. Remember that the standard form for the equation of a circle centered at the origin is given by x squared plus y squared equals r squared if r was the radius. R is positive. Now, if we divide both sides by r squared, we could, in principle, write this as x squared over r squared plus y squared over r squared equals 1. But remember that for an ellipse does not have a radius, r. So we're going to have two different numbers here. And that's where we get this. This is the standard form for the equation of an ellipse centered at the origin that is horizontal, or x long. X squared over a squared plus y squared over b squared equals 1. Remember, for an ellipse, a is not equal to b. There's no common radius. Now, it's a horizontal ellipse if the larger denominator, the a squared, is under the x squared as opposed to the y squared. So, for example, if we have on the top here, x squared over 9 plus y squared over 4 equals 1. This is the equation of an ellipse centered at the origin, and it's going to be x long. Now, it should be straightforward to find the vertices if you set y equal to 0, all right? The x-intercepts, the vertices will be intercepts here. If you set y equal to 0, you get x equals plus or minus 3. If you set x equals to 0 and get the y-intercepts, you get y equals plus or minus 2. So look at that. Again, you have x-intercepts, the vertices, at 3, 0 and negative 3, 0. And you have intercepts at 0, 2 and 0, negative 2. Now, these are not vertices. These are endpoints of the minor axis, but they're good points to know. So remember, in this form of the equation, all right, we have a squared and b squared in the denominators. A squared equals 9, so a is 3. That's why the x-intercepts here are at 3, 0 and negative 3, 0. B squared is 4, so b is 2. That's why we have the y-intercepts here at 0, 2 and 0, negative 2. And again, because the larger denominator is under the x squared as opposed to the y squared, it's a horizontal or x-long ellipse. Now, if the larger denominator is under the y squared, then we would write it as x squared over b squared plus y squared over a squared equals 1. Again, you would have positive numbers beneath the x squared and the y squared, but this time the larger denominator, the bigger number, is underneath the y squared. In that case, we have a y long or vertical ellipse, like so. So we have a units from the center to these vertices up here and down here, and b units to these endpoints of the minor axis over to the right and to the left. So for example, look at this. X squared over 4 plus y squared over 9 equals 1. The larger denominator, the 9, is under the y squared, so it's going to be y long. Okay, and look at this. The vertices are going to be on the y-axis here. That's the major axis over here, right? We get the vertices at 0, 3, 0, negative 3. Okay, a is 3, so we have vertices at 0, 3, 0, negative 3. B squared is 4 now. B is 2. And remember, a and b are positive by definition. If b squared is 4, then b is 2. 2 units over here, and then 2 units over here. So, and this is a y long or vertical ellipse. The larger denominator, the 9, is under the y squared, not the x squared. Okay. So these are two different ellipses, right? If you switch the denominators, then yeah, you can go from the red ellipse to the blue ellipse and vice versa. Now, you can also change the center of the ellipse. In forms 1 and 2, the center was the origin. But just like in chapter 1, we can use the principles of translation to write more general formulas. If the center is at h, k in general, right, then we substitute or replace x with the quantity x minus h in both formulas, and we substitute or replace y with the quantity y minus k in both formulas. So for example, let's say we want to move the center from the point 0, 0 to the point 1, 2. We move the center from 0, 0 to 1, 2. H is 1, k is 2. H is 1, k is 2. So if we take this ellipse centered to the origin, right, And if we go over here to the third equation, where we substitute x with x minus 1 and y with y minus 2, the same denominators, don't forget the squares, or the equals 1, we go from the red ellipse to the green ellipse, where the center is now at the point 1, 2. Now, what about the ellipse in blue? That centers at the origin, 0, 0. What if we want to move this ellipse, translate it so the new center is 1, 2? Well, once again, going from the blue marked ellipse here, we substitute x with x minus 1, substitute y with y minus 2, and we move the center from the origin to 1, 2. Remember, there are sign flips. Because we have x minus h and y minus k, we have sign flips. If we substitute x with x minus 1 and y with y minus 2, we move the center from 0, 0 to positive 1, positive 2. Whoops. No, that's correct. All right. So we go from the blue ellipse to the purple ellipse. The center moves from 0, 0 to 1, 2. So these are the more general standard forms for the equation of an ellipse centered at a more general point h, k. Remember, a squared corresponds to the bigger denominator, and it indicates whether we have an x-long or horizontal ellipse or a y-long or vertical ellipse. Don't forget the equals 1 on the right. The eccentricity of an ellipse describes how elongated the ellipse is, and is defined as c over a. So for example, and again, we can think of a circle as being like a degenerate ellipse just for the sake of argument, all right? For a circle, c is 0. It's like the foci collapse onto the center. C is 0, and therefore the eccentricity is 0. In fact, for a circle, the eccentricity E is 0, even though we don't call a circle an ellipse. Here, we have a slightly elongated ellipse. E is 0.3. So the center is fairly close. Sorry, the foci here are fairly close to the center. They're much closer to the center than the vertices are over here. Basically, the foci are 30% away from the center compared to the vertices and their distances from the center. The distance here is 30% of the distance here. E is 0.3, so we have slight elongation. If E is 0.8, we have substantial elongation. Okay, C is 80% of A. C is 80% of A. The distance from the center to each focus is 80% of the distance from the center to each vertex, which indicates strong elongation. Now we have comets that have very eccentric orbits where E might be 0.999 something. The sun, by the way, would be at one of the foci. That's one of Kepler's laws. All right. So E for an ellipse can be a real number circling between 0 and 1. Remember that C, the distance between the foci and the center, must be less than A, the distance between the vertices and the center. The foci are closer to the center than the vertices are from the center. So we know C is less than A, and they both have to be positive by definition. If we divide all three parts by A, 0 divided by A is 0. C divided by A is E. That's how we define E, the eccentricity formula. By the way, E here is not 2.718. It couldn't be for an ellipse. E here is for eccentricity. A divided by A is 1. So E, the eccentricity of an ellipse, is a real number circling between 0 and 1. The closer it is to 0, the more circular the ellipse is. The closer it is to 1, the more elongated the ellipse is. So these are the various pieces for analyzing an ellipse in the XY plane. Next, we're going to work with an equation of an ellipse directly.
All right. Any questions about the anatomy, terminology, notation for an ellipse? Any questions about that before we get to this Big Daddy problem? Okay, the kinds of thing you'll see in the homework. Any questions? Any questions? This last video is the last required video for the day, and then we'll have some fun game show stuff with Pascal's triangle. But the next video is the last required video, and you can do all the homework through 10.3.
Hi, everyone. I claim that this here is the equation of an ellipse. Let's put this in standard form and analyze the ellipse. Graph 9x squared plus 4y squared. And by the way, one hint that it might be an ellipse is that we have an x squared term and a y squared term in here. They're on the same side and the coefficients are the same signs, but they're not equal. If they were equal, we'd be more likely to have a circle. All right, 9x squared plus 4y squared minus 54x plus 40y plus 37 equals 0. So x squared and y squared are the highest powers of x and y in this equation. Find the center, vertices, foci, and E. I wouldn't have you actually graph on an exam, but in principle, if you have all this information, you should be able to. Now, our first step to get to standard form, remember standard form is going to look like one of these guys, right? First, we're going to group the terms. We're going to group the stuff in X and the stuff in Y. So we group the X squared term and the X term over here, the Y squared term and the Y term over here, separate with a plus sign. And then we subtract 37 from both sides. So I'm grouping these two, grouping these two, and then I'm subtracting 37 from both sides. So the non-zero constant is on the right side. Okay, so group in X and X squared, group in Y and Y squared, non-zero constant over here. And don't forget that right side, by the way. And then for each of these groups, we factor out the leading coefficient. Now, even if this were like a negative 55, or if this were like a plus 39 or plus 41, even if we end up with fractions inside here, you always factor out the leading coefficients. You have no choice. So here, you factor out a 9 from this group, even if that leaves an ugly fraction in here. And from here, you factor out a 4. Again, even if that leaves an ugly fraction in here. In this case, we don't leave ugly fractions. We have 9 times the quantity, x squared minus 6x. It turns out we complete the square with a plus 9. Then we have plus 4 times the quantity, y squared plus 10y. It turns out we complete the square with a plus 25. Equals negative 37. And then we'll discuss these later on. Now over here, to complete the square, remember we take the coefficient on x, here it's negative 6. We take half of that, we get negative 3. The sign doesn't even matter because we're going to square at the end anyway. But half of negative 6 is negative 3. When you square negative 3, you get positive 9. There's always a plus sign in here. Likewise, in here, we take the linear coefficient. The coefficient on y is 10. Half of 10 is 5. The square of 5 is 25. So we insert a plus 25 over here. But we can't just put in numbers because we feel like it. We have to pay for them. In this case here, we're going to balance things out. We're going to pay for these insertions over here by making adjustments on the right side. So now, if we insert a plus 9 inside here, are we really just adding 9 to the left-hand side? Well, the thing is, look at the 9 out here. When we insert a plus 9 inside the parentheses here, we're actually adding not just 9, but 9 times 9 by the distributive property. So that's why when we insert a 9 in here, we're adding not just 9, but 9 times 9, or 81. That's why I put plus 9 times 9, or you can put plus 81 over here. Likewise, over here, I'll put this in green, let's say. Let's put in green. Okay, the plus 25. When we insert the plus 25 in here, are we really just adding 25 to the left side? No, because there's a 4 out here, right? When we insert the plus 25, the 4 distributes in and hits the 25. So when you're inserting a plus 25 in this group, you're actually adding 100 because you're actually adding 4 times 25 to the left-hand side. Therefore, let's add 4 times 25, or 100, to the right-hand side. So because of this, we add 4 times 25, or 100, to the right side as well, because we've done that on the left by inserting a plus 25 in here. We're compensating. If we're adding 81 and adding 100 to the left side, we better add 81 and add 100 to the right side. Now factor these as factor, because bear in mind, when we apply CTS, we're developing these as PSTs. We're creating perfect square trinomials. Perfect square trinomial over here inside parentheses. Also, perfect square trinomial over here in parentheses. Now factor the PSTs, the perfect square trinomials, as squares of binomials. Over here, we have 9 times. Factor this, x squared minus 6x plus 9. That's a square of what? Likewise over here, 4 times the quantity, y squared plus 10y plus 25. This trinomial here, this perfect square trinomial, factors as the square of what? You can also simplify the right side. I'll give you a few moments. Factor, factor, simplify on the right. All right. X squared minus 6x plus 9 is a PST, factors as a square of x minus 3. You take this sign in here, the middle sign, and the square root of that. Basically, this should look familiar. It's the middle guy in the whole completing the square process. It's the negative 3 here. Plus 4 times, okay, this is the square of y plus 5. A key hint, half of 10 is 5, or the square root of 25 is 5. You take the plus sign in the middle over here. Equals negative 37 plus 81 plus 100 is 144. But wait, what do we need on the right-hand side? It's almost like matrices. What do we need on the right-hand side? We need a 1 on the right-hand side. How can I accomplish that? By dividing both sides by 144. Divide the left side by 144, that is each term. Divide the right side by 144, we end up with 1 on the right side. All right, when you multiply by 9 over 144, you're dividing by 144 over 9. Similarly, when you multiply by 4 over 144, you're dividing by 144 over 4. The only reason why I'm doing this is just in case you get uglier numbers down here. You could end up with fractions here. Like, for example, if that's a 145, you'd have 145 over 9 down here. Fortunately, these do simplify to integers. In fact, you could have gone directly like so. Right. 144 divided by 9. Okay, 9 divided by 9 is 1. 144 divided by 9 is 16. Over here, 4 divided by 4 is 1. 144 divided by 4 is 36. So we're lucky. We do end up with integers down below. We could have had fractions. That's why I did this. Of course, you don't have to do this on the homework, unless you actually do get fractions down there in the end. Okay, equals 1. Don't forget the equals 1. Again, this middle line here is not wrong. It's just that you might want to go straight from here to here. But if we had a 145 there, you would need this. All right. So we're done with standard form. This is in standard form for the equation of an ellipse. All right. Where's the center of the ellipse? Quick. Where's the center of this ellipse? A nice trick, which also works for circles. What point, what values for x and y, what ordered pair will make the left side equal to 0? That's a nice trick. Positive 3, negative 5. What makes the left side equal to 0? X equals 3, y equals negative 5. another way of looking at that, the top here, okay, you look at the x minus 3, so the form x minus h all squared, where h is 3. X minus 3 is of the form x minus h, where h is 3. Likewise, y plus 5, that's what all squared? Okay, so y minus h all squared. The square of y plus 5 is the square of y minus what? Well, when you add 5, you're subtracting negative 5. When you add 5, you're subtracting negative 5. K is negative 5. But the easy way to look at it, what makes the left side equal to 0? All right, 3 comma negative 5. Cast of characters. Take a look here. Which denominator is bigger? Is it the denominator in the x fraction or the denominator in the y fraction? It's the denominator in the y fraction. So because the 36 is our a squared, is the larger denominator, we have a squared equals 36, which means a is what? A is plus or minus 6, but by definition, a is positive, so we zap that symbol. A is 6. And this indicates, now because that a squared is the larger denominator, that means that we have a y-long or vertical ellipse. We have a y-long or vertical ellipse because the denominator here is bigger. A squared is 6, therefore a is 6. Over here, this is a smaller denominator, but we can still use it, right? B squared is 16. What's B? B equals plus or minus the square root of 16, or 4. But remember, by definition, A, B, C, and E, for that matter, are all positive, right? A, B, C, and E are all positive. We zap the plus minus. Of course, H and K themselves can be negative, the coordinates of the center. But A, B, C, and E, they're all going to be positive. All right, again, we have a squared equals 36 under the y square stuff, so it's y long. Right? A is 6, b squared equals 16, therefore b is 4. Find c. Remember that handy formula. C squared equals a squared minus b squared. A squared is 36, b squared is 16. We actually do need these things over here. C squared is 20, therefore c equals plus or minus the square root of 20, but we zap the plus minus, right? We originally started the plus minus, but then we zap it. Z is by definition positive. The square root of 20 simplifies to 2 root 5, right? 4 divides 20 nicely. 4 is a nice perfect square, comes out as a 2. Root 20 is root 4 times root 5, or 2 root 5. All right, observe that this is less than A. This is about 2 times 2.2, which is about 4.4. That's still less than A. Right. Find the eccentricity, C over A. C is 2 root 5, A is 6. Simplify, we get root 5 over 3. If you round that off, that's about 0.745. So fairly elongated, not too elongated, but fairly elongated. Right. So we sketch the graph. Again, I wouldn't do this to you on a final exam, but you should know the anatomy of this. You should know what points are involved here and these various parameters. All right. Again, for good show, let's graph this on Desmos. 9x squared plus 4y squared. Let's see if we can do it. 9x squared plus 4y squared minus 54x plus 40y plus 37 equals 0. How do you like that? Desmos does it. Sounds like a campaign ad. Desmos does it. The center is at, what was it? It was at 3, -5. All right, looks good. All right. Oh, it's a y long ellipse, vertical y long ellipse, because the bigger denominator was under the y stuff. All right. We have all this information. Okay. Now, from the center, how do we get the vertices? Well, it's a y long ellipse, so the vertices lie above and below the center. Okay. It's a y long ellipse. So the major axis is vertical and contains these 5 key points: the center, the 2 foci, and the vertices. The center is at 3, -5. The vertices are 6 units away. A equals 6, okay? That affects the vertices. Okay? That means that from the center, we walk up 6 units to get one vertex, we walk down 6 units to get the other vertex. Now, the center is 3, -5. Which coordinate stays the same on this vertical major axis? The x coordinate stays the same, x equals 3. It's the y coordinate that's changing. It's kind of like the frame method for trig functions. If you take y equals -5 and you add 6, you get +1. If you take y equals -5, if you subtract 6, you get -11. It's a lot like the frame method for y coordinates in trig. Let's plot these points, 3, 1, and 3, -11. Good, and 3, -11. Good. This is all very comforting. We have the center right now and the 2 vertices. Now for the 2 foci, it's similar to calculating where the 2 vertices are, except that when we change the y coordinate, we don't add A, we add C, right? That's the distance from the center to each focus. We add C to the y coordinate, we subtract C from the y coordinate. So the coordinates of the foci go 3. All this is happening on the vertical line x equals 3. Here's the vertical line x equals 3, right? That's the axis, the major axis. The major axis lies on there. Okay, and these are the y coordinates, right? So 3, -5 plus 3, -5 plus 2 times square root of 5. That's up there. And 3, -5 minus 2 times the square root of 5. That's the blue point down there. These are the 2 foci. If you want to draw this ellipse, get a taut string of length 2a, as it turns out, the major axis. I'll show you that. Okay, put thumbtacks at the edges. You can sweep out this ellipse if you keep the string taut. All right. The eccentricity is about 0.745. It's fairly elongated, as you see here. Wow, that's a lot of information. Oh, label here, right? So again, these 5 key points, the center, the 2 foci, and the 2 vertices on this major axis of this y-long or vertical ellipse. It's like the mall in Washington, D.C. And then if you wanted the endpoints of the minor axis, all right, you would take the center and you change the x coordinate. You would change it by 4. So you add 4, 3 plus 4 is 7 over here, 3 minus 4 is -1 over here. So -1, -5, and 7, -5. Again, if you take the center, -7, -5. There you go. Okay. Again, to get those points, we share the y coordinate this time. They're on the horizontal line y equals -5. These points share the same y coordinate. The x coordinate changes. From the center, 3, you add 4 to get the 7 here, subtract 4 to get the -1. 4 was B, the semi-minor axis. By the way, this A is called the semi-major axis. B is called the semi-minor axis. All right. Next time, what explains the formula for C that we used up here? Next time.
So here's the game plan. At this point, you can do all the homework on chapter 9 and on 10.3. And to be honest, if you have to go, you can go. Now, what I'm going to do next is I want to show you the magic of Pascal's triangle and Plinko, this game show from The Price is Right. It's one of the key reasons why I love being sick from school in 4th grade. And then if you're interested in asking me questions, around 9:35, I'll be done with this stuff and I'll open it up for questions. All right, so I'll go ahead and pause and let's play. Plinko is Pascal's triangle. Let's go back over here.
Believe it or not, this here is Pascal's triangle. One of the favorite games on The Price is Right.
Go back here.
This triangle. Plinko is Pascal's triangle. Let's go to this great website, mathisfun.com, which does a great job with Pascal's triangle. So how is Pascal's triangle constructed? You might remember this from your algebra class. So you start off with a tent of ones. So you have ones along this edge and ones along this edge, like a pyramid. Now, every time you have two consecutive numbers, they give birth to their son, their sum. So for example, here, the 1 and the 3 give birth to a 4. So up here, 1 and 1 give 2. Over here, 1 and 2 give 3. 2 and 1 give 3. And then here, 1 and 3 give 4, as they show. 3 and 3 give 6. 3 and 1 give 4. By the way, one of the properties of Pascal's triangle is that it is symmetric. If you draw an axis here, you see the left and the right mirror each other. The left half and the right half mirror each other. And Pascal's triangle is gorgeous. There are so many patterns. Of course, you have ones along this diagonal. You have the positive integers on this diagonal, the triangular numbers. Imagine dots like 1, 2, 3, right? On this diagonal. Again, we have symmetry, left side and right side. If you add up the sums, and we'll see why this is true, 1, 2, 4, 8, 16, and so forth, powers of 2. And there are reasons for that. Surprisingly, exponents of 11 are hidden in here, powers of 11. The Fibonacci sequence, remember, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5. Each successive Fibonacci number is the sum of the two prior Fibonacci numbers. It's a famous sequence, and it's also hiding in Pascal's triangle. If you shade in all the odd entries, and you do it for many rows, you get the Sierpinski triangle or gasket. It's this thing, which is a famous creature in chaos and fractal theory. The idea that basic rules lead to these elaborate, complex patterns. Okay, now we saw the powers of 2 before, and this kind of explains why. For example, consider 3 flips or tosses of a coin, fair or not, right? Well, how many possible sequences of 3 heads or tails can we have? Well, we have 3 flips or 3 positions. Each position can be a head or a tail, right? So we have 2 possibilities for the first flip, 2 possibilities for the second, and 2 possibilities for the third. 2 times 2 times 2 is 8. Now, Pascal's triangle, let's look at this. 3 flips or tosses of a coin, fair or not, all right? Notice there's only one way to get 0 tails and 3 heads, 3 ways to get 1 tail and 2 heads, 3 ways to get 2 tails and 1 head, and only 1 way to get all 3 tails. These are the numbers in Pascal's triangle on row number 3. Bear in mind, when you look at Pascal's triangle, row number 0 is on top. So row number 0 has the 1. Here's row number 1, row number 2, row number 3, and so forth. You can look at the second number in the row to see what row number we're talking about. Now, it turns out that Pascal's triangle is this list of binomial coefficients over here. N choose K, or NCR. Do you remember those numbers? Remember 52 choose 5, or 52 C5, the number of possible poker hands from a deck of 52 cards? That's 52 choose 5. That's way down in the table in Pascal's triangle, but it's there. So basically, if you're like Vanna White on another game show, if you flip these binomial coefficients around, these NCR values, you're going to get Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so forth. Here are the first 15 lines of Pascal's triangle, rows 0 to 14, and the ancient Chinese knew about it. I want to go back to why it is that these binomial coefficients, these NCR numbers, the number of combinations of n items taken r at a time, like poker hands, why they correspond to Pascal's triangle. All right. Well, again, this is why it's Plinko. Let's go back to this Plinko board over here, this Pascal's triangle. All right. In fact, I'll go to the very top. All right. So how many ways are there to hit this pin over here? Imagine that each of these squares corresponds to a pin. How many ways are there to hit this pin over here? 3, choose 1, or 3. Left, left, right, left, right, left, and right, left, left. We're imagining these falling chips. How many ways are there to hit this pin over here? Only one way. Left, left, left. Well, there's one way to hit this pin and 3 ways to hit this pin. How many ways are there to hit this pin? 1 through here, and then go right, 3 through here, and then go left, 4 ways to hit this pin. So the number on each of these squares, these numbers in Pascal's triangle, they correspond to the number of ways that the chip can hit that pin. Let's go back here. Why is this 3, choose 1? 3, choose 1 is 3, all right? So 3 drops, n equals 3. A right is a success. Right is a success. So left, failure, right, success. That's one way to get 1 success and 2 failures. Left, failure, right, success, left, failure. Again, another way to get 1 success and 2 failures. 1 right, 1 success, 1 left, a failure, another left, a failure. So how many ways are there to get 1 success and 2 failures out of 3 trials or 3 drops? 3 ways, 3, choose 1. So that's an example of why Pascal's triangle is a table of these binomial coefficients, the number of combinations, NCR, n items taken r at a time. Again, 52 choose 5 is way down here, about 2.6 million. At the very bottom, again, the Plinko board. It's called a quincunx. So let's say that it's 50-50. P is 0.5 in a binomial distribution. Let's speed it up. Here, n equals 6, p equals 0.5. And we're looking at what a binomial distribution, where n equals 6 and p equals 1/2, what that histogram would look like.
P is a probability of a success. It's really a stats video.
And take a look at this. It's looking more and more bell-shaped. What if we up it to 15? N equals, let's restart this. N equals 15, p equals 0.5. Sped up, looking down there. N equals 15, p equals 0.5. Binomial distribution. Again, a right is a success, a left is a failure. Each drop is a trial, which means that these numbers here correspond to the number of successes. If you're a student who gets all 15 questions correct on a true-false exam, for example, then you'd be in this bin over here. Not very likely, though. And again, it looks more and more bell-shaped. All right. And they explain the quincunx over here. Again, it's a great website. Great website. Okay, and a normal distribution approximates that. But Pascal's triangle is absolutely gorgeous. Pascal's triangle, which is one of the most beautiful things in math. I talked mostly about it last time, but I wanted to add in a few finishing touches here. This is a handout I created about the magic of Pascal's triangle. So as a quick reminder, remember we put ones along these edges of this tent or pyramid here, right? And every time we get 2 consecutive numbers, they give birth to their sum. Their sum is a sum. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, and so forth. And I claimed that these numbers in Pascal's triangle were in fact these binomial coefficients, these numbers of combinations, n choose r. So for example, 3 choose 1 is 3. And that corresponds to the number of ways for a Plinko chip to hit the 3. There are 3 drops, n equals 3, drop, drop, drop. Okay, a right is a success, a left is a failure. So how many ways can you get 1 success out of 3 trials, 1 right out of 3 drops. Well, left, left, right, left, right, left, and right, left, left. 3 choose 1 is 3. Now, how is this related to the binomial theorem from algebra? So you might remember from algebra class that a plus b all to the third can be written like this, right? Where for the variable parts, we start with a to the third, we decrease the exponent by 1 until the a disappears, and then for b starts off as b to the 0, which is 1, which is invisible, and then we get b to the second, b to the third. And the coefficients for this power of a binomial, right? These coefficients come from Pascal's triangle. It's these binomial coefficients, these n choose x guys. N choose 0, n choose 1, n choose 2, n choose 3. 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1. Now, why does that make sense? How do we get the cube of a plus b? Well, if you cube anything, you take 3 copies of that thing, here, a plus b, and you multiply them together. And you can distribute like crazy. But basically, when you perform the distribution, for each term, you get a choice from here, a choice from here, and a choice from here. It's kind of like if you have 3 meals in a day, breakfast, lunch, and dinner. For breakfast, you can pick super salad, A or B. For lunch, A or B, super salad. For dinner, A or B, super salad. Okay, now, again, instead of salad, we can talk about B, or a success, or getting a question right, or getting ahead, okay? So basically, if you choose a term from here, and then choose a term from here, and then choose a term from here, there are 8 ways to do that. 2 times 2 times 2. 2 to the third is 8. So you could have all soup, right? A. That could be all failures. The number of ways to get 0 successes out of 3 trials. The number of ways to get 0 questions correct on a 3-question exam, 1 way. Wrong, wrong, wrong. A is wrong, B is right. But how many ways can you get 1 question right and 2 questions wrong? How many ways can you get 1 success out of 3 trials? Well, you could have wrong, wrong, right, wrong, right, wrong, and right, wrong, wrong. When you add these together, you get 3 a squared b. The 3 here is the number of ways to get 1 question right out of 3 questions. Likewise, 3 choose 2 is also 3. That's from symmetry. The number of ways to get 1 question right out of 3 is equal to the number of ways of getting 1 question wrong out of 3, or 2 questions right out of 3. So there are 3 ways to do that. You add these up, and you get 3ab squared. These 3 guys here. And then there's only 1 way to get all 3 questions correct on a 3-question exam. Correct, correct, correct. That's b cubed. Add these all together, and you get the expansion of the cube of a plus b. So if you love algebra, I'm sure you love that.
All right, so that's all I had to say about that. All right, so lots of ideas there. So for many of you, had to have a good weekend, but I'm sure that some of you have questions. So let's go ahead and put this away. All right, at this point, I'll take questions. Okay, all right. So, okay, 8, 1, 7, and 12. All right. Yeah, I'm pretty sure on this one, 7 has infinitely many solutions because these are equivalent equations. It's the same line. So yeah, if you were to go to Desmos, for example, x plus 3y equals 6. Negative 2x minus 6y equals negative 12. Negative 6y. Yeah, it's the same line. Right. So you have infinitely many solutions, every point on the line, basically. Now let me show that on the tablet. And by the way, I'm continuing to record, but if you don't want me to record, just let me know. Okay, so let's see. All right, so in this one, let's do this in green. All right. Yeah. Okay. So in case you're curious how Gibbs works out on this Gauss elimination. All right. So on 8.1, number 7, what happens? So now again, you should write down the original augmented matrix, right? So we have 1, 3, /6, and we have -2, -6, /12. All right. Now we like the 1 there. I want to make the -2 into a 0. So what's the idea? We take the old row 2. It's good to write down this these notes. The old row 2 goes, it went, whoops, -2, -6, /12. And then we want to add twice row 1. 2 times 1 is 2. 2 times 3 is 6. 2 times 6 is 12. And lo and behold, when we get our new row 2, check this out. 0, 0, 0. So the new row equivalent matrix looks like this. 1, 3, /6, 0, 0, /0. And in fact, that would be in row echelon form, actually. That is in row echelon form. But then what's the corresponding system? The variables or unknowns were x and y, right? Okay, so we have x plus 3y equals 6 and 0 equals 0, right? So any solution x comma y has to satisfy both, but 0 equals 0 always holds. That's irrelevant. That's superfluous. So really, this has infinitely many solutions, all the ordered pairs that satisfy this. In fact, technically, if you do an ordered pair, if you do this in set builder form, it's the set of all ordered pairs x, y. You have to write this, but it's the set of all ordered pairs x, y, and R2 such that x plus 3y equals 6. You didn't have to write that. But basically, any ordered pair in R2, which is real comma real, basically, the set of those ordered pairs, any ordered pair that satisfies this equation, okay, will be a solution. And if you look at if you consider the graph, right, okay, basically every ordered pair corresponding to every point on this line will give us a solution. We have infinitely many solutions corresponding to infinitely many points on that line. Right. So that's more of a concept question. There are infinitely many solutions. Just by virtue of the fact that these are equivalent equations. In fact, I would have just accepted that. But I showed you what the augmented matrices said, right? We get something weird going on here, right? Any questions about that before I go on to your 12? Before I go on to number 12? Okay, yeah, that was a weird one, right? I know people have trouble with the weird ones. Okay, so 12. I think I started that with somebody. Let me try to reconstruct the notes on that. Actually, I'm gonna leave this up here and then. Oh yeah, I'm going to my old ones. Yeah, 8112. So I did part of this. Wait, that's 814. 8112, that's here. Right. Okay, yeah. So here, oh yeah. You're having trouble with the unusual ones, right? The degenerate cases. So okay, here, this is the augmented matrix, right? And I'm using row 1 to change row 2. I want to make that 5 into a 0. But right off the bat, look at this. We're getting this strange row here. 0, 0, 0 slash -4. Now, we can stop right there. You don't have to go to row echelon form because we know we have a weird case here. Wait, what's the equation that corresponds to this? It's 0 equals -4. If this thing's going to have a solution, then we must live in a world where 0 equals -4. But we don't live in a world where 0 equals -4. This is indirect reasoning. The solution set is the empty set. And you can stop right there. You don't have to do any more matrices. You don't have to go to row echelon form. You can short circuit it right there. Right here, you know that we're dead as far as solutions go. The empty set or null set is the solution set. Okay. So right, you're having a difficulty with the questions where we did not have a unique solution. And that's the case for many students. All right, any questions about that or any follow-ups? Right. Any other questions? Any other questions? Oh, you're very welcome. Yes. Any questions? You're welcome. Yes. Have a good weekend. I'll hang on for another minute and then I'll take a 3-minute pause. So at 9:45, I'll call a pause. Any questions? Get cracking on that homework.